thank you very much. And let me start by thanking the organizers for the opportunity to present this talk, which is based on work done in collaboration with Paolo Di Vecchia, Rodolfo Russo, and Gabriele Veneziano. So the idea is to present some techniques that allow us to calculate classical gravitational observables, in particular associated to the cold scattering events, and eventually to touch base with gravitational waveform templates, starting from a slightly unconventional point, namely by taking the classical limit of quantum field theory scattering amplitudes, which, as we shall see, involves a resummation technique known as the iconal exponentiation. So let me start with a few words of motivation. Experiments like LIGO and Virgo have opened up a new field of gravitational wave, let's say, spectroscopy, the possibility to understand the complicated objects by studying the spectrum of their emitted gravitational waves. And this, of course, calls for the need of precision waveform templates. So here I'm drawing a cartoon of a typical waveform emitted by a black hole merger event. So initially we have a so-called in-spiral phase in which the two massive objects are still sufficiently far apart, and they orbit around each other for a very long time, emitting weak gravitational waves. Eventually, these two objects plunge towards each other, towards the merger proper, and this eventually leads to the formation of a bound state. Now, what I want to emphasize is that while the merger in itself is a regime of strong gravitational interactions where nonlinearities of GR really are important, and therefore this is the realm of numerical relativity simulations, in contrast, the in-spiral phase is still a perturbative regime. In particular, two different types of perturbative schemes have been devised in time. One is the so-called post-Minkowskian regime, which is, as a slogan, an expansion in powers of G, or more precisely, an expansion in the weak gravitational interactions, more precisely in terms of this small parameter, Gm, the typical size, the Schwarzschild radius of the sources of these two objects, divided by the typical separation. And another framework, perhaps more conventional one, is the post-Newtonian one, which exploits the fact that not only gravitational interactions are weak in this in-spiral, but also velocities are comparably weak according to this equivalence dictated by the virial theorem. So it's let's say, a joint expansion in powers of G and V squared. Now, I'm going to focus here on the post-Minkowskian framework. And in fact, I'm not really going to talk about mergers, but rather about scatterings. So aside from being interesting in their own right, this type of events have been not yet observed, actually, by our detectors. So we may wonder what we can learn from this type of events about the merger events instead, which seem to be happening more frequently. And let me make two remarks in this direction. So the first remark is that if we manage to evaluate the effective potential interaction, the conservative quasi-instantaneous force that acts between the two objects in GR, this VF, then we can in fact export it, or export more precisely the corresponding effective Hamiltonian directly from the unbound case to the bound case. And another observation goes in the direction of analytic continuation. So for instance, if we manage to calculate the deflection angle for the scattering, so between the incoming and the outgoing velocities, then we can analytically continue it and obtain the precession angle for the closed orbits. Now, an observation, mainly due to Zwieber and collaborators, is that scattering amplitudes in quantum field theory are to some extent naturally suited to tackling the post-Minkowskian calculations. And the reason is that they are already organized. In fact, the only way we know how to calculate scattering amplitudes is by organizing them in powers of G, which is precisely the post-Minkowskian expansion. And they stay generic in V because they are Lorentz invariant. And so, of course, they can treat all velocities democratically. So today, I would like to focus on a particular puzzle that arose in this type of framework relative to the calculation of the deflection angle at 3 p.m., so order G cube. And the puzzle is the following. So Zwieber and collaborators in 2019 evaluated this effective potential I was telling you about from the G to the cube amplitude and extracted from it the 3 p.m. deflection angle for a scattering of two massive non-spinning objects in particular. And if we regard this angle as a function of the energy of the collision, its impact parameter V, which sizes the relative separation, asymptotically and the two masses, then we take the high energy regime, what we find is the following. So together with the expected g times e over b to the power 3, which is just this small post-Minkowskian expansion parameter, there is also a logarithm, which seems rather puzzling because it seems to be diverging at high energies. And moreover, this plainly contradicts the corresponding massless result, which was derived in 1990 by Amati, Ciaparoni, and Veneziano. So, of course, one would expect that the high energy regime of massive scattering would be smoothly connected to the massless scattering, so the deflection angle between two shock waves interacting gravitationally, but this didn't seem to be the case. And in fact, this result was rather strong, this massless result. It was argued to be universal, not only true in general relativity, but also in more in setups with more supersymmetry, for instance, in a maximally supersymmetric setup of n equal 8. So today I would like to describe how this calculation of the scattering angle can be performed, and eventually this puzzle can be solved. And to do that, I will have to introduce a little bit how we go about taking the classical limit of the scattering amplitude, particularly going through this iconal exponentiation, and how we connect this iconal to the deflection angle. And then I will illustrate the results, in particular in the supersymmetric case, which is much simpler from the amplitude point of view. And then hopefully at the end, I will have time to mention how we connect instead with the real life case of GR. So let me begin by specifying a little bit better the problem under consideration. We want to consider the classical scattering of two objects with weak gravitational interactions. So we have to specify, let's say, a hierarchy of length scales. For instance, we can impose that the Compton wavelength of these objects should be much smaller than their proper size, typically their Schwarzschild radius. And this imposes for us the classical limit. In turn, both these length scales should be much smaller than the typical separation here sized by the impact parameter, and this guarantees that gravitational interactions be weak. Now, the object from which I want to extract information is this 2-to-2 scattering amplitude involving indeed the scattering of two objects with masses m1 and m2, and which we usually calculate in momentum space, so as a function of the energy, center of mass energy, and the transfer momentum. Now, the first step we need to perform is that in order to make contact with this impact parameter, we want to perform a Fourier transform from Q to B and express the amplitude as a function of S and B rather than S and Q. And of course, in Fourier transform, this regime in which the impact parameter is effectively very large translates to a regime in which the transfer momentum is effectively very small. More precisely, we are allowed to not only to expand for small q in momentum space, but actually to disregard any analytic piece that we have for small q, analytic in q squared, because this would, of course, give rise to strictly localized contributions in position space, whereas we are interested in the long range parts of the amplitude in 1 over b. So let's do just that. Let's take the amplitude, perform the Fourier transform, and go to impact parameter space and see what we find out. So here I'm presenting the form of the results schematically in terms of these length scales, the Schwarzschild radius and the Compton wavelength, but in order to make dimensional analysis much easier, but let's say that we can expand in G and power count in G and in H bar. So at 3 level, we find an amplitude that has this 1 over lambda, so a 1 over H bar, as expected from the standard counting, right, in which the powers of H bar should be the number of loops minus 1. So 3 level should be 1 over H bar. Now, what happens if we go to 1 loop? So order G squared, as you can see here, R squared in these terms. Well, we not only find terms that are indeed quantum, in the sense that they have either H to the 0 or H to some power, positive power, but also again 1 over H bar terms, and in fact even worse, 1 over H bar square terms. So let's say classical and super classical terms, and the situation of course gets even worse at 2 loops where we have not only these classical terms again in green, the green box, but also super classical and doubly super classical terms. So we need some way of making sense of all this, and the proper way to do it is to make an ansatz for the right asymptotics of the amplitude in the classical limit, which is the following. We expect that the amplitude should scale as should behave as a rapidly oscillating exponential, e to the I over H bar times the classical action, which is encoded by this exponential here, which is the exponential of the iconal phase, small delta. And then downstairs, the amplitude should only have a weakly varying, slowly varying remainder. So in particular, this delta should only have a 1 over h bar, or r over lambda in terms of a dimensionless quantity. And then this big delta instead should only have h bars to the 0, to the 1, and so on. Once we have identified this proper semi-classical limit, we can, however, in order to compare with the amplitude, which you only know how to calculate for small g, formally we have to re-expand this ansatz, re-expand it for small g, and then indeed we find precisely the structure that I was showing in the previous slide. So we have a leading order tree-level which has a 1 over h bar, this delta 0. Then we have a square that arises from the exponential, right, when you expand the series, and this is what gives rise to these doubly classical or super classical pieces of the previous slide. And of course, the structure goes on, and by comparing this writing with the previous one, we can effectively determine from these green boxes the delta we are interested in, the small delta, which contains this classical phase. Very good. Once we have determined this, what do? We can go back from impact parameter to momentum space. And now in this Fourier transform, after resummation in impact parameter space, we see that the momentum at which the Fourier transform peaks is the one determined by the stationary phase approximation, so by this derivative of the iconal phase. And then, of course, once we have determined the transfer momentum, it's a simple matter to extract the deflection angle chi we are after. So one last warning before going to the results. The warning is that I've been calling small delta a phase, and this is indeed true at order g and g squared, but this is no longer the case at order g cubed, which we are interested in. In fact, small delta 2 as an infrared divergent imaginary part. So, and in fact, I hope to be able to come back to this at the end. It will be, in fact, crucial for extending the derivation from n equal a to gr. But for the moment, let me notice that this real part prescription that comes from the stationary phase approximation does away with this problem, and we don't have to care about this imaginary part for now. So now, if one manages to do this calculation, the final question is, does the coefficient we get here in front of this gm over b to the cube, does this coefficient have the famous log I was mentioning at the beginning? Now, of course, I don't want to go into the details of the calculation, which requires some technical ingredients. I want just to mention a couple of these ingredients, which are important in order to compare with the calculation by Bern et al. I started from. So, of course, at some point we face the issue of evaluating some loop integrals. I showed here just a sample, this double box integral, and we would hardly have simplified the problem with respect to a purely classical calculation if we needed to compute this integral exactly and then evaluate the small q limit, which, let me remind you, is tied to this 1 over b expansion that we have in the post-Minkowski regime. So luckily, we can exploit the technique known as the method of regions and easily evaluate the series expansion of this integral in the small q limit before doing the integral, luckily. So there are essentially two regions that matter. One is this hard region, which comes from the integration region, which are very large compared to q. Let's say that the order of the masses. But this only gives rise to terms like q squared to the 0, q squared to the first power, which are analytic in q squared, and therefore which can be safely neglected if we want to, if we are interested in the long range behavior of the result. The soft region instead, which is the region in which the integrated momenta are of the same order as the transfer momentum q, which we are taking to 0, these instead give rise precisely to these non-analytic terms I'm showing here, and therefore they are the relevant ones. So the calculation we want to do is we take the amplitude, we expand the loop integrals in the soft region, we go to impact parameter space, and we evaluate the iconal. And from the iconal, we can evaluate the scattering angle. So what is the difference with respect to the calculation by Bern et al., the one which had the famous log? Well, in that case, you remember the calculation of the scattering angle went instead to the calculation of this effective potential. And in order to take into account only conservative parts of the interactions, a further truncation of the integration was performed. So not this full soft region here, which is the relevant one for us, but rather a sub-region of that called the potential region was considered. So, and this is defined essentially by truncating the integration to off-shell intermediate gravitons, or in equalate where we have more states, to off-shell intermediate force mediators. And instead, a complementary region called radiation region was neglected because this was due to on-shell mediators, and therefore it was not relevant to the calculation of the effective potential. So let me show here the result for n=8 supergravity. Here I'm drawing also a cartoon of all the loop integrals that matter for this simpler amplitude compared to the GR1. Let me mention that, of course, n=8, although simpler, has the same puzzle. So if you restrict to the potential region and you calculate the effective potential, you also find this logarithmic enhancement. And here I'm showing the result for the full 3pm iconal, evaluating the full soft region. So taking into account not only potential, but also radiation integration regions. And the result is the following. Here in red, I have these terms that also appear in the potential region, the conservative ones. And here in blue, I have the new ones that we find in the soft. And the corresponding ones, of course, are given here for the angle. Now, we are in a position to answer the question that we posed at the beginning. What happens if we now take this result, which is for generic energies, sigma, I forgot to mention it, it's related to the velocity of the particles, and we go to high energy. So in the high energy limit, what happens is the following phenomenon. The two types of terms, the potential ones and the radiation ones, talk to each other. And in particular, the logarithm of V squared that emerges from this inverse hyperbolic cosine of sigma gets a factor which is not 1, but is suppressed by another inverse power of the energy. So the two contributions separately would have this logarithmic enhancement, and indeed the potential contribution, as shown by Bern et al., does have this logarithmic enhancement, but the sum of the two, in the sum of the two, the logarithm cancels. On the other hand, the first line combines neatly to reproduce the result by Amati, Cefaloni, and
Carlo,
Veneziano.
you have 5 minutes,
Thanks.
maybe less than 5 minutes.
Thanks a lot. And combines neatly to give the Amati, Cefaloni, and Veneziano result, and restores perfect agreement with the massless case. So the significance of these new terms, although I've already hinted at it a minute ago, is it becomes more manifest if we instead take the near static, the small velocity limit, if we go to the PN post-Newtonian regime. And it's the following. So the potential terms have only even powers of the velocity for small velocities, whereas the new radiation, let's say, terms have odd powers of the velocity. So they are not time reversal invariant. And this is a clear signal that this is due to a non-conservative force, which is the so-called radiation reaction force. It's due to the fact that these bodies actually emit some gravitational waves, and they, of course, they feel some effective force. They decelerate a little bit because they have emitted energy. So the punchline of this is that in order to restore the agreement between the massive case at high energies and the massless case, one cannot neglect the radiation reaction force in the scattering. So let me mention very quickly, I described how the puzzle is solved for n=8, but what about the real life case of Einstein gravity? Do we need to redo the calculation all over again? So in principle, we can start from the amplitude and redo all the steps I've described. Well, luckily for us, we can take the result for the conservative part of the scattering angle, of the deflection angle, and add on top of it just the radiation reaction part. And this can be done by a trick. So by noticing that this imaginary part, which had this infrared divergent term, in fact, is precisely contains this correction that we need, in particular to the iconal. And so it's very easy it's much easier, let's say, than calculating the full amplitude to just evaluate this 1/epsilon piece of the iconal at 3pm, and then take this prescription, multiply the imaginary part by minus pi epsilon and send epsilon to 0. And with this trick, we managed to easily extend the n=8 calculation also to GR. So let me just wrap up. Again, let me reiterate that the radiation reaction effects are crucial in order to retrieve a smooth limit for the deflection angle at order 3 p.m. from the massive case to the massless or the high energy case, and that studying this imaginary part of the iconal is in fact very useful in order to include this radiation reaction effect systematically, both in N=8 and in GR. So thank you very much for your attention.
Thanks, Carlo, for staying within the allocated limit and for the nice presentation. Questions? I'm scanning through to see if there are any.
I see a hand by Eligio.
Ciao, yes, Eligio is there.
Okay. So you started with by mentioning merger events in the perturbative regime. Maybe it's my fault, but I lost the connection with merger events. So from this calculation, what do you gain in the understanding of these events?
Yes, so I tried to address it in this slide. So I sort of warned you that I would change topic from what promised in the first slide. So of course, gravitational scattering can be interesting in its own right. Of course, people are actually doing this kind of simulations and see if we manage to observe some gravitational scattering via gravitational waves. Still, you may complain, as you probably have in mind, that we have not observed it so far. So maybe it would be better to learn something about the closed orbit setup. And essentially, the answer is that you can analytically continue this scattering angle at 3 p.m. and obtain the precession of the quasi-elliptic orbits. So you can basically go from energy larger than zero, which you know is associated to these hyperbolic-like trajectories that we are considering in the scattering, and obtain the corresponding terms in the precession of the orbit.
So you are saying that at least in perspective, you can gain more information also on closed orbits.
Exactly. So the idea is that these two approaches are to some extent complementary, right? Because of course, for each order in the post-Minkowskian series, you can in principle re-expand it for small v and compare with the post-Newtonian expansion, which is usually performed for bound orbits, where v squared is of the same order as g. For the moment, to be completely honest, I don't think that these post-Minkowskian calculations are competitive. So they do not, you know, if you re-expand these results, you do not really add to the state of the art of the post-Newtonian calculation, which have been going on for quite some time. And I guess to become competitive with these results, one should go quite higher, like, I don't know, I think 7 p.m. should be the first one, which becomes really state of the art also for post-Newtonian calculations. But yeah, the idea is that it's worth pursuing for this reason. Yes, that you might be able, for instance, to do some integrals that people were not able to do in the other setup, coming from the amplitudes.
Thank you.
Thanks, Carlo. I have a very, I would like you to stay, you know, brief in the answer, but you know, similar computations, I actually was happen to have done it in. You do it also in gauge theory when you look in the iconal approximation, you know, for pattern distribution functions, right? So you actually do that too, and you have the iconal approximation there too. It's not an approximation; you can calculate in like cone. So how different is how different do you think this is from actually in a computation that you do in quantum field theory, where you resum technically all the photon exchanges? I mean, should be the same, right?
I can say there's just two very quick things. So one is that they are conceptually very similar, because as you are saying, you are also resumming, you know, these drawings are precisely the ones you would have in mind. Also, that you resum multiple ladder exchanges. The difference is, of course, that one expects gravity to be weak at large separations, right? Whereas the opposite is true in the QCD setup, right?
No, but talk about QED.
Ah, sorry, QED. I
QED. Yes,
no. The situation QED is very similar. In fact, the radiation reaction force, you can also calculate it in the same way. It just happens to be Yeah, we
actually calculated that, but 10 years, 15 years ago.
Yeah, exactly. So it's very similar. You're right.
All right. So, more questions? If not, I will thank again Carlo for the